Okay, let's talk about torque. You've heard the word thrown around, right? With engines, with wrenches, definitely in physics class. And it seems simple enough. It's just a twisting force. But there's this one little detail that trips up almost everyone. It's direction. You know, that arrow on the diagram that seems to point in a completely random, nonsensical way? Well, today, we're going to solve that mystery once and for all. Here's how we're going to do it. First, we'll nail down the basics with a simple twist. Then, we'll get hands-on with the famous or infamous right-hand rule. After that, we dive headfirst into the vector problem, the heart of the confusion. But don't worry, because right after, we'll reveal the brilliant 3D shortcut that makes it all click. And finally, we'll see why it all connects. All right, let's start at the beginning. Section 1, a simple twist, from pushing to turning. So at its absolute core, torque is just the rotational version of a regular old push or pull. You know, in physics, we sometimes simplify things and pretend objects are just points. But torque deals with reality, things that can actually turn and pivot and spin. It's really just a way to measure how good a force is at making something rotate. Think of it this way. A linear force, that's like pushing a box, and it slides across the floor in a straight line. Simple. But a torque? That's what you apply to a revolving door. You're still using a force, but the result, the outcome, is rotation. That's the whole game with torque. Okay, so on to section 2, the right-hand rule. And it is, quite literally, a handy convention. See, since torque causes rotation, it's a vector, which means it has to have a direction. And physicists came up with this really clever and very physical way to figure it out. It's the right-hand rule. And seriously, don't be too cool for this. Actually do it. Take your right hand. Point your fingers out from the center of, say, a bolt, along the wrench. Now curl your fingers in the direction you're pushing. Boom! Your thumb is now pointing in the direction of the torque vector. The key thing here is to remember this is just a convention. It's a rule everyone agreed on to make things work. And that brings us to section 3, the vector problem, the mystery of the perpendicular force. This is where it all gets weird, because when you use that right-hand rule, your thumb points somewhere that makes no sense at all. So here's the big question. If you're turning a steering wheel, right, the force is circular, the motion is circular, everything is happening in this flat circle. So why on earth does the math say the torque vector points straight out of the wheel at your face? It's totally perpendicular to everything that's actually moving. It just feels wrong. And hey, if that question is scrambling your brain, you are in very good company. A Reddit user on the physics forum put it, well, perfectly. Okay, but why? This is, without a doubt, the single biggest hurdle for people learning about torque, and for a very good reason. Okay, you ready? It's time for the aha moment. Here's the deal. The reason that vectors seem so bizarre isn't because the physics is weird. It's because we're thinking about its job all wrong. It's not describing motion. It's actually a brilliant mathematical shortcut. This is the most important part, so let it sink in. The torque vector is not telling you which way anything is moving. The wrench is not going to fly up towards your thumb. That arrow has nothing to do with the path of the force. So what does it represent? Well, it represents the plane of rotation. Just think about it for a second. In our 3D world, what is the absolute simplest, most efficient way to describe a flat spinning disk? It's a single arrow sticking straight out of its center, perpendicular to the surface, right? Well, that arrow, that's the torque vector. It's just a shorthand, a symbol for that entire spinning plane. And here's the perfect real-world example, a standard nut on a bolt. Lefty-loosey, righty-tighty. If you turn the nut counterclockwise, that's the rotation, which way does it actually travel on the bolt? It moves outward along the axis. The direction that nut travels is the direction of the torque vector. It's a physical version of that abstract perpendicular arrow. And this clever little mathematical trick actually has an official name. It's called a pseudovector or an axial vector. So unlike a true vector, like velocity, that points in the direction of motion, a pseudovector points along the axis of rotation. It's this beautiful convention that lets us use the simple math of vectors to describe the much more complicated idea of a spinning plane. It's a shortcut that just happens to work perfectly in 3 dimensions. So, let's bring it all home. Let's recap this whole journey from being completely confused to hopefully having that light bulb moment. So you see, the confusion was never really with the physics itself, but with the language, the mathematical language we use to describe it.
That weird perpendicular vector isn't a force or a movement, it's just a label. It's an elegant mathematical shortcut that encodes the entire idea of a spinning plane into one simple arrow. And that makes handling all this complex 3D motion a whole lot easier.
It really makes you wonder, doesn't it? The next time you run into some physics rule that just feels bizarre or counterintuitive, maybe ask yourself, is this a fundamental law of how the universe works? Or is it a clever shortcut, a convention that we humans made up just to help us describe the beautiful, complex world all around us? Definitely something to think about.